a slightly different day. We'll have, as usual, two speakers. First one will be Souvik and then Prasanna. So the format is, as always, we have 20 minutes talk and then 10 minutes questions. And in between, we have a coffee break of 10 minutes where you can join a breakout room and get a coffee and talk to other participants. Okay, then let's get started. Souvik will go first. Can you please start sharing your slides?
Can you see my slides?
Yes, that's good.
Yeah. Okay. So,
Floor is yours.
yeah. Okay. So, firstly, I'm very sorry for asking a different time due to my personal problem, and thank you very much, everyone, that you have made your time and finally allowed me present in my according to my convenience. Just a second. Okay. So, this paper is about, as the title says, strategy-proof probabilistic assignment rules with endowments. So the main departure or the main added thing here is the probabilistic thing, the probabilistic assignment rules. So this paper is with three co-authors. Let me start in the reverse order. So Dr. Shomurup Sadhuka is my former PhD student. Now he is a faculty at IIT Kanpur in India. Then Sri Durga, Dr. Gogulpati Sri Durga, she was not my formal PhD student, but she worked with me as a PhD student, and I see her as my PhD student. Now she has graduated. Now she is a faculty at IIT Hyderabad. And Sai Pranith Donthu, he is a project student of Shomoru. So in a sense, my grand student at IIT Kanpur. And do you know how to, something is blocking my screen. Okay. Florian, okay, okay.
So you can't
Yeah,
skip.
yeah, now it's okay. Something was blocking my screen, but now it has disappeared. Okay, so I have 34 slides, but most of these slides are not needed for this presentation because probably we know most of the basic things. And some of the slides are regarding some extension of the work that I'm going to present. Those also I may skip if I do not have time. So into the introduction is that we consider assignment problem. Think of some real life example, like we all are faculty members in some department. We all have our offices, but we are not quite happy with our offices, or we are not like the happiest with our offices, and we would like to shuffle our offices to be better off or to feel happier. So the point here is that we all have some initial endowment, which is one office is already given to us. And we also have some preference over the all possible offices. We assume strict preferences. I will tell you if the preferences are weak, how things can be extended. And no monetary transfer is allowed. So it's not a mechanism design per se problem. It's a pure matching or social choice problem. And in this framework, there are three main properties considered, or desirable properties considered for this problem. So the problem is, once again, we have our offices, we want to reshuffle our offices. So we want to have, there is one current assignment, and we want to come up with a different assignment, which is in a sense better. But better means, in what sense better? First of all, strategy proofness. Second is Pareto efficiency. Third is individual rationality. So these definitions, I think, is clear to everyone. I will formally define for the timing. If you know this, the meaning of this definition, then it's okay. I'll say just wait. So the question is that I want to find an allocation, assignment, an improved assignment, which satisfies these three properties. And when the initial endowment, which I have just discussed, which is determined that case, already it was proven by Ma in 1994 that the TTC, top trading cycle, that is the unique rule that satisfies all these three properties. And then very recently in Ekichi or Ekichi, I do not know how to pronounce it, so very sorry for that. So in 2024, it's a theoretical economics paper. In this paper, he shown that if you weaken Pareto efficiency by pair efficiency, I will formally define all these things, then also you get TTC rule as the unique rule. Okay. So that's the background. That's the whole background. Now, what we are going to do, we are going to allow for probabilistic outcomes. I'll define formally what probabilistic outcome is, but just to motivate you or just for you to see what we are going to do, the people may not get, initially they all have deterministic endowments, but finally they may not get one rule. We may get a probability distribution over the offices. And then final allocation will be decided through some random experiment as it is done in probability theory or in any real life lotteries. And the motivation here, why should we consider probabilistic rule? Because definitely it's fair. It allows for many different rules, many scope of optimizing the welfare, depending on how you define the welfare. So there are many reasons. It's very well known in the literature why probabilistic rules are important to consider. And how we model the probabilistic outcomes, we model it through bistochastic matrices. So rows you can think of as us, the faculty members, the columns are offices. We assume same number of faculty members and the offices because we all have one distinct office, so that has to be the case. And then in this matrix where rows and columns are as I have defined, if you assume that each cell has a probability, which means it's a fraction, such that the row sums are 1 and the column sums are 1, then it's a bistochastic matrix. And this type of outcomes we are searching for. And we are going to define the desirable properties because now outcomes are probabilistic. We need to define preferences over probability distributions. Maybe incomplete, but we need to do that. That we will do. And then we will see what are all probabilistic rules that satisfies these three properties. One important note here that we consider the initial endowment to be deterministic. So initially we have one deterministic endowment. It's kind of realistic, not 100% I would say, because even if the initial endowment, even if it has come through some probabilistic method, but still after there is a probability distribution, there has to be some sampling and then people have got the initial endowment and they are resetting. So once we are using some office, there has to be some deterministic. It's not that I probabilistically every day I use different offices. So that way it is quite enough realistic, I would say. I will also tell you why initial endowment need not be deterministic and what are the problems there. And we will also discuss some open problems in this framework. Now, the basic model, I have already explained you the model, but still I'll very quickly go through the model. We have n number of agents, n number of objects. Each agent has a strict preference, which we denote by PI, the preference of the ith agent. The initial endowment, it is deterministic without loss of generality. I will assume that agent I owns xi, the object, and it is deterministic. So it's a one-to-one function from n to x. And because the cardinalities are the same, it becomes bijective anyway. The set of all deterministic assignments we will denote by n. And a deterministic assignment rule is a mapping from the collection of all preference profiles to the set of all deterministic matching assignments. So basically, once this rule, what it does, once you give it the preferences of all the agents, it will give you an allocation or assignment. So it will tell you that you will get this office, you will get that office, and so on. That is what this rule is going to do. Now, top trading cycle, I'm not going to explain here. It must be clear very to all of you. But just the idea is that starting with the initial endowment, we are looking whether it can be made better for everyone. It means that some people are strictly happier, some people are okay. And if it is not, then we'll let people that, okay, whoever are not happy, you people tell me how you want to shuffle. These people say, and I modify, then again I allow other people. And so that this process converges, there is a monotonic. There is a direction to it, how I do it. That is basically top trading cycle. So you basically start with any assignment. In this case, we'll start with the initial endowment. And every time you let people report the possible modification for them, and you will let them modify. And you go step by step, being careful that it will converge so you do not do repetition and so on. Anyway, I'm giving you this intuition behind TTC because it will be, at some point, I will get back to it. And this example is not, I'm not going to the details of this example. Now the properties. Three properties we are going to deal with. One is Pareto efficiency. Pareto efficiency means that once I give you the endowment, it must not be the case that some people can be strictly better off and everybody else can be weakly better off. So there cannot be an overall improvement. Because if there is an overall improvement, then there is a better social welfare that way, and I'm not doing a good job by deciding the assignment. Thus, Pareto efficiency, again, was quite standard. Individual rationality says that you cannot punish someone by giving some office which is worse than his or her current office. So my current office is my right. If you give me something better, I will go, but not otherwise. That's individual rationality. So the final outcome must be as good as my current office. Strategy proofness is again is the most common object in this literature. It says that if you misreport your preference, you cannot get something better. So you cannot manipulate the rule. Mathematically, it says that whatever you get by reporting your preference truthfully will be as good as RI means weakly preferred to whatever you may get by misreporting your preference. That's strategy proofness. Now, as you see, you may remember that I mentioned this Ekichi paper 2024. In this paper, only the Pareto efficiency was weakened to pair efficiency. Okay, I have given some alarm. So, Florian, I think I still have 10 minutes, right? Roughly, or?
Yes, 10 minutes.
Yes. So you see this Ekichi paper, they have weakened Pareto efficiency to pair efficiency, and that paper was very much valued. So in this paper also, we tried all possible weakenings just by understanding that these are important. So let us first discuss this weakening of Ekichi 2024. So Pareto efficiency means that no group of people can be better off by reshuffling their offices. Pair efficiency is a weaker or stronger condition, whatever way you want to say it. It says that no two people can shuffle their house and be better off. So Pareto efficiency is a much broader condition. It's a weaker condition. If my rule is Pareto efficient, I know that two people cannot collude or two people cannot shuffle their rooms. If it is pair efficient. If it is Pareto, then I know much bigger thing. Now, technically it is very clear that pair efficiency is much weaker than Pareto efficiency, but sometimes, in this mechanism design thing, two notions which apparently look not quite similar, one is stronger, but they turn out to be the same, or they turn out to have equal impact. But here it is not the case. Pair efficiency is indeed much weaker than Pareto efficiency. So this is one example. I will not go through the example. It's a very obvious example, but this example shows that that some assignment can be Pareto efficient, but not Pareto efficient. So pair efficient, but not Pareto. So here P1, P2, P3 are the three preferences. X1, X2, X3 means pair 1 or agent 1 prefers X1 to X2, X2 to X3. And this blue color, it is shown their assignments. And this is the outcome. So pair agent 1 gets X2, agent 2 gets X3, and so on. So this outcome is pair efficient. No two pair can shuffle and be better, but it is not Pareto because you can give them their best outcomes. So that's why it is not Pareto efficient. There are numerous examples in this paper, and we have also given some examples where it is shown that there are so many pair efficient outcomes, but which are not Pareto efficient. So pair efficient is a, I would say, it's a big weakening in a sense, strong weakening or something like that. Now, the known result, Ma has shown that if you want to have Pareto efficiency, strategy proofness, and individual rationality, then TTC is the only rule. This is in the deterministic setup. And then Ekichi in 2024 shown that if you weaken Pareto efficiency by pair efficiency and keep the other two conditions, you still get TTC. Okay. Now, what we are going to do is, so you may be a bit surprised that, okay, Pareto efficiency was weakened by pair efficiency, but you cannot get out of TTC. But you can wait for a much, bigger surprise. So now we are working with probabilistic assignment. Everything remains the same. Only the outcomes are no more this deterministic assignment. They are bistochastic matrices. And the ith row of the bistochastic matrix, it denotes the probabilistic outcome of the ith of agent I. So for instance, if a 3 by 3, if ith row is 1/3, 1/3, 1/3, then I get row of is 1 with 1/3 probability, of which 2 with 1/3 probability, and so on. Now, because outcomes are probability distribution, now I need to define preferences, maybe incomplete, over probability distributions. And in the standard literature, we do it using stochastic dominance. Roughly speaking, it says that one probability distribution stochastically dominate another. There are two ways to see that. One is to see that if every upper contour set, if you don't know the upper contour set, it means that every top set, according to your preference, must get weakly higher probability than the other. So I prefer one probability distribution to other. If for the first probability distribution, if I fix any top set according to my preference, top means top few, say some top rank, say top 1, top 1, 2, top 1, 2, 3, and so on, then the probability for the first probability distribution will be at least as much as the second probability distribution. Another way to say it is that for any utility representation of my preference, the expected utility from the first probability distribution will be at least as much as the second probability distribution. So these are the two ways to see stochastic dominance. Again, I'm not spending much time because this is also, I think, very familiar, well-known to people like us. Or in the last 10 minutes, I will come back if you need any more clarification. Now, once you introduce the stochastic dominance comparison, the Pareto efficiency or pair efficiency or individual rationality or strategy-proofness, everything you can do. For all these things, you just needed some preference. Now we have a preference, which is stochastic dominance. Stochastic dominance preference extension is not complete, but no, it doesn't matter. Still, on the part you can compare, you can define all these notions. Okay. So before I said that this is preferred to that, now I say stochastically preferred to that, like that, just the change of notion. Now, as I've said that we are going to weaken things as much as possible. You see, strategy-proofness, it says, think of the deterministic part. It says that you cannot be better off by misreporting your preference. That means, for instance, you are now getting your fourth ranked object. By misreporting, you cannot get third or second or first. We are going to define a very restricted version of strategy-proofness. We are saying that by misreporting, you cannot get your top. If you're not getting your top, you will not get your top by misreporting. I'm fine if you get from fourth to third, I don't have a problem. So much, what I should say, much lesser requirement, much weaker requirement, which we call top strategy-proofness. And in the probabilistic setup, you will manipulate only if the probability of the top ranked object is increased. Otherwise, you don't care. Okay, so you just care about your top best. With respect to that, if it improves, then only you will manipulate and misreport accordingly. We'll also consider two different domains. One is FPT and FTT. FPT, the full name is free pair at the top domain. It says that for every two alternatives, say X and Y, there must be a preference in the domain which places X at the top and Y as the second. So I'm not requiring all possible preferences. You know, in social choice, if I have, as the designer, if I have a knowledge about the preferences of the people, I can stop them from manipulating. I can get more rules. So I'm trying to have more rules. I am considering stochastic dominance extension. I'm considering probabilistic rules. I'm considering domain restriction. One is FPT and another one is free triple at the top, which says that if you have three objects, X, Y, Z, then there exists a preference in the domain which places X first, Y second, and Z third. Now our main theorem. Consider FPT domain. So free pair at the top domain. I'm not asking all the other results in the deterministic setup. They were requiring full set of preferences, unrestricted set of preferences. I'm just requiring FPT domain, and I'm considering probabilistic rule. I want SD Pareto efficient, SD individually rational, and SD top strategy proofness. Of course, strategy proofness is stronger, the result will be true. Just as weak as possible, as general as possible. But as I said, the very surprising result we get is that we still get just the TTC rule. Okay, once again, we tried to weaken everything possible, but we still are back at TTC rule. Now we'll do even more. Now, if in place of SD Pareto efficient, if you want to have SD pair efficient, the domain has to be a bit more richer. Instead of FPT, you now need FTT, free triple at the top. But then again, you get TTC rule. In particular, the earlier result for unrestricted domain, where everything is possible, we get in the probabilistic setup with pair efficiency, individual rationality, and top strategy proofness, you get TTC rule. So in a sense, whatever was improved in the AKC 2024, okay, we also have improved things much more beyond that in a sense. Of course, with due respect to his paper, I don't mean to anything. Idea of the proof, I will not go. Now, some other side results. There are another notions of this efficiency. I have discussed Pareto and pair efficiency. There is one notion which is called ex post efficiency and individual irrationality. Ex post notions are based on convex combination of deterministic outcomes. So I say some probabilistic outcome ex post efficient if it is a convex combination of deterministic efficient outcomes. So I have a probabilistic outcome. If I can write it as convex or probability mixture of, I see that. I will get back. I see there is a thing. Just a second. So okay, I think I have just 5 minutes. I will complete. So exposed notions are based on convex combination of deterministic outcome. I will say something exposed efficient if it is a probability mixture of deterministic efficient outcomes. Only thing you need to note here that exposed, the set of exposed whatever, efficient, individually rational, these are bigger set. So again, I am hoping that I am, instead of stochastic dominant Pareto efficiency, I am now allowing for exposed efficiency. Maybe I will get something better. But the answer is that no. With 3, these are equivalent. This exposed efficiency and SD efficiency, they are all equivalent. With 4, they are not equivalent. But again, we show that you get the same result. Okay, it's written somewhere that with exposed notion, you get the same result.
We're actually pretty much out of time, so
I'm done. I'm done. There are some open questions, but during this 10 minutes discussion, I can get back to this. I'm done.
Okay,
Hello.
thanks.
Yeah.
Let's give a round of applause to Souvik. Please unmute yourself and clap.
Thank you.
Okay, so then we have time for questions.
Yeah.
There was a question in the chat by Dominic. Dominic, do you want to ask yourself?
Yeah, so we are in a probabilistic setting, but then you're characterizing TTC. Is that deterministic TTC? And so the result implies that probabilisticness does not actually help to satisfy these axioms?
Yes. So yeah, that's exactly the case.
Okay, thank you.
If it's doable, can you say a little bit about like how you get that it's deterministic?
The outcome, like the idea of the proof?
Yeah, if you have
Yeah. I don't know. I can explain that. But before that, let me say, you see some major open questions I was about to state. Let me tell you one thing, one very important thing. If the initial endowment is random, then it's a very difficult problem. The reason it is difficult that sometimes there are no rules. It's a bit surprising. So it is already known in the literature that with some initial random, purely random endowments, for instance, uniform, the initial endowment is uniform. Everybody owns everything with equal probability or equal proportion. Then with n equals to 4, with 4 agents and 4 objects, there are no rules that satisfy all these properties. Okay. And also you may note that when the initial endowment is random, TTC cannot be defined. Defining TTC is a problem because TTC starts with you are sitting in some office and then pointing to some other office and so on. And I mentioned that because the proof idea or the concept why I get deterministic thing that has some thing to do, some connection with this fact. So roughly why we cannot have really a probabilistic outcome satisfying all these properties is that suppose think of a preference profile. Everybody is getting for contradiction. I'm saying some people are getting really probabilistic outcome. Now they have some individual endowment, initial endowment. If you put the initial endowment right at the second place, then you know that they will get either the initial endowment or they will get their top, some probability to the top alternative. So starting from the preference profile, I'm going to another preference profile where with respect to initial endowment, there is exactly one office that you prefer. Now, at this profile, either I have to, with some probability, you will stick to, I have to give your initial endowment, or I can give some probability to your probabilistic thing, to your top. I'm going to a separate preference profile. But then with some tweak combinatorics, you can show that at that profile, and now we can sense that it's a very tough profile. You really cannot give any probabilistic outcome. The second part is that now, step by step, you can show that starting from what arbitrary profile I have started with, there also you cannot give a probabilistic outcome. So, roughly speaking, giving probabilistic outcome gives the chance for people to manipulate by moving their initial endowment towards the top and getting all the probabilities to the top. That is a way of manipulation they can do, and to stop them, I cannot give really probabilistic outcome. But with the initial endowment random, it's a very difficult problem. With different endowments, we are getting different types of rules. We cannot define TTC. Very complicated algorithms we can define. We can show that those one, two particular algorithms are satisfying all these properties, but no characterization at this moment as of now. We have very many results there. We are still working, but no characterization still.
Peter?
Thanks for the presentations and Happy New Year. You mentioned this von Neumann theorem that if you have a doubly stochastic matrix, it's a convex combination of permutation matrices. Is that step efficiently performable algorithmic? Since if the outcome of your computations is a doubly stochastic matrix and you want to transform it into a probabilistic distribution over assignments, you have to make that step effective. So is the result by von Neumann algorithmically efficient?
Okay, thank you for this question. Actually, this result doesn't help because the problem is, let me tell you something more. Let me take 2 minutes. This is a very important question. I have something written there also, but let me not get there. So when we are working for probabilistic initial endowment is random. Then we tried this approach that the initial endowment can be broken into deterministic endowments because these are bistochastic metrics, convex combination. For every deterministic, I know the probabilistic, the outcome through TTC. So I take the same probabilistic combination of the deterministic TTC outcome and I get something which might be satisfying all these properties. The unfortunate thing is that this doesn't give efficiency. So if I take probability mixture or convex combination of deterministic permutation matrix or deterministic bistochastic matrix, the resulting matrix doesn't satisfy efficiency. So this method actually for efficiency, this method somehow I would say it doesn't help. It was our initial guess to proceed that way, but it doesn't help directly. We did not use this fact anywhere in the proof also.
Okay, but my question basically is this decomposition. Can that be computed efficiently? See, Dominique is already answering the question.
Yeah. So I think then the answer is no, because you can have all the deterministic matrices efficient, but the convex combination is not efficient.
Okay, but I see my question has been answered by Dominic in the chat. Thanks.
Okay. Sorry. Maybe I didn't get the question. Very sorry.
So one other issue with using this decomposition to extend TTC to deterministic to probabilistic endowments is that the decomposition is not unique. Right? So
No, it's not unique. It's not efficient. So, for instance, one way, first of all, the initial endowment is random, then you cannot, TTC is not defined. But what you can do is that initial endowment, you break it into deterministic endowment. For each endowment, you can apply TTC. Then you can combine the TTC outcomes. The efficiency will be violated. That's the very big problem. So that way, it doesn't like help in our analysis. Is the thing clear? So convex combination of efficient outcomes need not be efficient. That is a big problem for this analysis.
Maybe just to briefly explain, I think there was a confusion by efficiently implementable. I think Peter meant can you write an algorithm that gets the decomposition quickly.
But it is a very important question. So when we were working with random endowments, I initially said because they were my students, I said that okay, initial endowment is bistochastic. You break it into deterministic. For every deterministic, you know the outcome. You take the same probability combination, you will get everything. But then we checked that it is not becoming Pareto efficient.
Aurelio, unmuted yourself. Do you have a question? Okay. Any other questions? Okay, then let's move on to the coffee break. So you will have the chance to join a breakout room and talk to people there for 10 minutes, and then we'll resume with a second presentation.
Thank you. Thank you very much. I'll be there for the second presentation as well. Thank you.
Second speaker is Prasanna, who will tell us how to appease a majority of voters. You also have 20 minutes. The screen is yours.
Thank you very much, and thanks everyone for coming. I assume everyone can hear me okay? Great. Okay, so I want to mention this is joint work with four wonderful collaborators, Moses, Alex, Adrian, and Kangning. So the typical setup that we have in this problem, which probably most of you are familiar with, is that we have some voters and we have some candidates, and the voters have some ranked preferences over the candidates. And so I'll represent the results of an election with a table like this. So this is an election with 10 voters and 5 candidates. And the first row of this table represents the voters' top choices, their first choices, and the last row represents the voters' last choices. And so with an election like this, the pretty typical question that's central in our area of social choice theory is how do we go about choosing the most broadly appealing candidate? And so the reason why we're so interested in this question is that it's worth remembering that there's quite a wide variety of decision-making problems that we make as a society that can be modeled as these kinds of elections. And so probably the most prominent example is in a political democracy where we have constituents choosing representatives. But you can also imagine like an organization making hires or choosing winners of prizes. And also very everyday decisions like friends choosing what board game to play or like where to go out to eat. You know, I always find it funny when we go to like a conference with a bunch of social choice people and you have to make a decision about something. You can really see the gears turning in the way that people ask each other what their preferences are. Um, and so, yeah, so there's a lot of different ways of viewing elections. And so with all of these different applications, we come back to this question of like, how do we go about choosing the most broadly appealing candidate? And so one reasonable principle to strive for is something like majority rule. So for example, if a majority of voters prefers candidate A over B, then it feels like we shouldn't choose B instead of A. That would be like a pretty undemocratic thing to do. But of course, we know that life is not so easy for us. And so there's something called Condorcet's paradox, which goes back to the 18th century. And it shows that there are actually elections where no matter which winner you pick, a majority of the voters will prefer one of the other candidates. And so the simplest example of this is just the following election, which is a cycle of three voters whose preferences follow this cyclical ordering of three candidates. And so here, if you choose candidate one, then a majority will tell you they prefer candidate three. If you choose candidate three, though, then a majority will tell you they prefer candidate two. And if you choose candidate two, then a majority will tell you they prefer candidate one. So any candidate you pick, a majority will prefer one of the other candidates. And so this is kind of one of the earliest impossibility results in social choice theory. But actually, it turns out that even just this very innocent impossibility can get a lot worse. And so there's this thing that I like to call Condorcet's nightmare, which is that there are elections where no matter which winner you pick, 99% of the voters will prefer one of the other candidates. And the idea is very simple. If you just take a larger cycle of candidates like we have here, then if we choose any winning candidate, then all but one of the voters will actually prefer one of the other candidates. And so you make the cycle as large as possible, and the fraction of kind of unhappy voters will become arbitrarily close to one. And so this might seem like kind of a bit of a contrived example, but it points to a kind of unsettling possibility that no matter what decision we make, no matter who wins, basically everyone will be unhappy. And I think that, if you've ever been in charge of something, then you know how real this possibility feels. Um, and so what can we do about this? Well, we need to relax the problem in some kind of way. And so one idea is what if any one candidate will cause this kind of issue, what if we can choose multiple candidates called a committee in the literature? And so, for example, we can look at this right half of voters that are maybe particularly unhappy with this candidate we picked, candidate 5, and maybe they'd be a lot happier if we also chose candidate 10. And so now there's no longer a candidate that a majority of voters prefer over both candidate 5 and candidate 10. So we have at most 4 out of 10 voters that prefer candidate 4, and the same with candidate 9. But there's no longer a single candidate that a majority of voters can say that they prefer over all the candidates that we chose. Um, and so let me point out that just like there are a lot of applications of elections, this idea of committee selection is also very pervasive in a lot of the different social choice settings that we care about. So there are a lot of settings where it's actually quite natural to choose like multiple winners, like say for choosing grants or fellowships or choosing papers to accept at a conference, and hiring, ordering food, all these kinds of things. It's very common that you might make multiple choices. And you can also think of committee selection as a kind of pruning step, where maybe first you want to narrow down to a smaller subset of candidates. And so this idea of committee selection also shows up in a lot of these different social choice settings that we care about. And so with all this in mind, here's the problem that I'm going to tell you about today. And so we saw with Condorcet's paradox that it's possible that no matter what winner we choose, a majority of the voters will prefer one of the other candidates. And so the question is, what if we can choose multiple winners? Can we choose K winners such that less than 50% of voters prefer any alternative candidate over all of the winners? In other words, there's no losing candidate that a majority prefers over all of our winning candidates. And so naturally, we could do this if we just selected all of the candidates, but it would be nice if we could have the number of candidates that we choose be small relative to the total number of candidates. So is the question clear? Can I see some thumbs up if or nods? Great. Okay, and let me also point out that in some sense, this like 50% threshold for majority is a bit arbitrary, and so we can also ask more generally, for each value of k, what's the best value of alpha that we can guarantee here? And so I'll also just mention that one thing that I really like about this problem is that it feels like such a simple and natural question, something that you can imagine Condorcet asking in the 18th century. But on the one hand, it actually was only defined, by Elkin, Lang, and Safadine, I forgot to mention, in 2011. But also the tools that we use to tackle this problem actually would not have been available to Condorcet. And so the main tools that we use are game theory and the probabilistic method, which are only, maybe about 100 years old. And we also build on some very recent work on something called approximately stable committee selection by my co-author Kang Nang and some of his other collaborators. But before I get into all of that, let me say a little bit about some of the previous work on this problem. And so we saw that essentially with this question, Condorcet's paradox tells us that we can't do this with k equal to 1. One candidate isn't enough for a majority. And so what happens if we can pick two candidates? It turns out that two candidates is also not enough. Basically, the idea is that instead of having a single cycle in the preferences, you can take the product of two different cycles. And if you kind of set things correctly, then you can show that any two candidates you pick, a majority will prefer one of the other candidates. But sort of intriguingly, these kinds of examples don't rule out three candidates being sufficient for a majority. On the other hand, it's very easy to get an upper bound of logarithmic in the total number of candidates. And the argument is very straightforward. It's like a simple greedy algorithm. If you just take the candidate that wins the most pairwise majority votes, or the Copeland winner, then you can argue that that candidate has to beat at least half of the other candidates. And so if you just take this Copeland winner, remove the candidates that it beats, and then recurse on the candidates that beat our Copeland winner, then each step we cut the number of candidates in half. And so in the end, we get a logarithmic number of candidates in our set relative to the total number of candidates. And so the question is, what's the right answer between this 3 and log m? And I can tell you that my first instinct was that probably, this k should grow with the number of candidates. As you have more candidates, you probably need more candidates in your set. And probably I thought that this like logarithmic bound should be the right answer. But it turns out that this is not true. So we show that in any election, no matter the number of candidates or voters or the preferences they have, you can always choose at most 6 candidates, such that less than 50% of the voters prefer any alternative candidate over the 6 candidates that you picked. And so the title of the paper is actually 6 candidates suffice to win a voter majority, but I kind of didn't want to spoil the punchline in the title of the talk. More generally, what we show is that if you can choose k winners, then you can choose them such that less than alpha fraction of the voters prefer any of the alternative candidates, as long as alpha and k satisfy this sort of strange inequality, which you can just think of as a lower bound on alpha, that if alpha is sufficiently large, then we can do this. And if you compare it to kind of what this product of cycles thing shows that you can't do, then it's sort of correct up to this weird 1 minus ln alpha factor. But it might be a little bit easier to see what this is saying with a picture. And so here's a graph where these blue points represent, as a function of k, the value of alpha that we can get. And this red line represents what we can't do, this 2 over k plus 1. And so let me point out kind of a couple of interesting points in this picture. So here we can see that even with 2 candidates, you can actually get a value that's bounded away from 1. So you can satisfy all but maybe like 80% of the voters. And so in some sense, with just 2 candidates, you can actually avoid this nightmare 99% of the voters are unhappy situation. You can see that between 5 and 6 here, we cross the like alpha equal to 1/2 threshold. And if you make alpha like much larger, like say the number of Oscar Best Picture nominees, which is 10, then you can satisfy all but maybe 1/3 of the voters. A kind of funny piece of trivia is that actually before 2010, the number of Oscar Best Picture nominees was 5, which you can see is like a lot worse in this picture. And it turns out that the reason why they made this change was that in 2009, The Dark Knight wasn't nominated for Best Picture, and basically a huge number of moviegoers were very unhappy with this compared to the nominees, and so they convinced them to change the number of nominees to be larger. And so I think it's kind of amusing that very much the same sort of issue of a large fraction of voters preferring one of the other candidates over the candidates that they picked, resulted in them making this change. Any questions about this? Okay, so just to give you a very high-level overview of the proof, here's sort of my one-slide vision board of how the proof works. And so at a very high level, the first stage of the proof is that if we look at the randomized analog of this problem, where instead of choosing a deterministic committee of candidates, we can choose a randomized committee of candidates, then the problem becomes a lot easier. Basically because we can model this as a kind of game, and it's a lot easier to understand games where you can randomize over the strategies rather than when you have to pick them deterministically. And so this was done in the earlier work that I mentioned. If you're familiar with the concept of maximal lotteries or stable lotteries, this is what's going on here. In the second stage of the proof, the idea is what can you do with this randomized, this distribution over committees? The idea is to kind of use it as a sort of measuring stick. So rather than comparing candidates and committees against each other directly, you compare them against this kind of good distribution over candidates, where you basically ask voters, like, how likely would you be to prefer a candidate or committee over a random committee sampled from this distribution? And so it's kind of this cute idea where you can turn these ordinal preferences into cardinal preferences by asking these sort of questions like how likely would you be to prefer this candidate over this committee? And there's this sort of cute interpretation of this question as a sort of measurement of a certain area in a picture, which I can explain at some point if you're interested. But the nice thing is that it kind of creates a geometric view of this question, which makes it a lot easier to analyze. And so finally, the idea is that essentially what you want to show is that there's some candidate that, there's some committee that has a large area while all candidates have a small area. And you can do this by just arguing that a random committee actually has a large area in expectation. And because of this like nice geometric view, this argument turns out to be quite simple and straightforward. And so that's at a very high level how the proof works. And so like I said, I can tell you more about the proof if you're interested at the end, or also, there are longer versions of the talk linked on my website where I go into quite a bit more detail about this. But I thought it would be more fun to take a little bit of a digression and tell you about something, a cute connection that you might not know about, that I think that if you don't know about it, you'll find it very interesting. And so imagine that I pose you the following dice game. So I show you these 4 different dice, and we're going to play a game where the two of us are each going to pick one of these dice and roll the dice, and whoever has the higher roll wins the game. So the question is, if you get to pick your die first, which dice should you pick? Which of the dice is the best one to pick? And so it turns out that if you kind of walk through these different dice, you'll find that if you pick the blue die, then that's actually not such a good choice because the red die is going to beat it 2/3 of the time. On the other hand, if you pick the red die, then the green die beats it 2/3 of the time. And if you pick the green die, then the purple die beats it 2/3 of the time. And if you pick the purple die, then the blue die that we started with actually beats it 2/3 of the time. And so it turns out there's no good die that you can choose in this game. And these dice are called intransitive dice because they have this sort of intransitive property in terms of like which one is better than which. Um, and there's been a lot of kind of interesting work on intransitive dice, both from the math community and also in kind of pop math literature. A lot of this started with this article by Martin Gardner in 1970, where he talked about these dice I had on my last slide, which he learned it from this Stanford professor, Bradley Efron. And so there's kind of a funny story that often goes along with these, which is that apparently Warren Buffett is like a big fan of these dice, and he carries them around with him and uses them to trick his friends into paying for lunch. Um, and there's a story that goes that one time he was trying to do this with Bill Gates, and so he poses him this game and says, here are the dice, you can take first pick. And then Bill looks at them for a couple of minutes and does some math, and he says, actually, no, maybe you should pick first. And so this is a kind of funny story, but once you know the trick, it's sort of no fun because you know that the game is always rigged against the person who has to choose first. And so maybe we can make it a little bit more interesting and give the first chooser a bit of a leg up. And so what if we allow them to pick multiple dice and then take the best roll out of the dice? The question is, can the game still be rigged? Can you design some different dice so that even if the other person can pick multiple dice, then they're going to lose this game more than half the time? And so you might see where this is going. And so it turns out that this is all a voting problem in disguise. And so if you think of the dice as candidates, and you think about each point in your sample space as a voter, each possible roll of the dice as a voter, and then the order of the dice in each of those samples as the preferences. So then this voter kind of prefers the green over the blue over the purple over the red. then the phenomenon that every die loses to one of the other dice more than 50% of the time is exactly the same phenomenon that every candidate loses to one of the other candidates for a majority of voters. And so actually, these intransitive dice are just a very particular example of Condorcet's paradox, with some very particular independence in the way that the voters' preferences are. And I thought this was a really interesting thing that I was surprised that I'd been working in social choice theory for so long before I learned about this. And it really changed my perspective on the area because I'm so used to social choice being about, people's preferences. But in some sense, there's no people having preferences in this example. And so I thought that was really interesting. And so kind of analogously, there's a dice version of our result, which is that with any arbitrary dice, even if the dice can be arbitrarily correlated with each other, then 6 dice is enough to gain an advantage in this game. And it turns out that, this is actually completely equivalent to the problem. And so, if you're in a conversation with someone and they ask what you do and you don't really want to talk to them, you can always tell them you work on correlated intransitive dice. Okay, and so let me just spend a couple minutes with a couple of concluding thoughts. And so there's a lot more work to be done, so we haven't fully resolved the problem. And so in our paper, we conjecture that the lower bound is the right answer. So we think that we can always choose k candidates such that at most 2 over k plus 1 fraction of voters prefer any of the other candidates. And so in particular, we think that 3 is the right answer to get a majority. There's been some progress on this recently. So there's a nice new paper by Song, Nguyen, and Lin that's going to be in SOTA this weekend, which shows that you can improve the 6 candidates to 5. And I'll also point that a very interesting special case here is just the case where k equals 2. So if you can just pick 2 candidates, I'd really love to know what's the right answer you can get here. And basically, our best bounds are now between 2/3 and 3/4. And this really feels like something that one should just be able to, get your hands on and solve, but it turns out to be like a lot trickier than it sounds. There's also a lot of interesting directions on kind of stronger conditions that you can hope to guarantee. And, this is something that we've been thinking about and working on. So you can check out some of our more recent work if you're curious about that. And so with that, I'll conclude with some takeaways here. Thank you very much, and I'm happy to take any questions.
Okay, thanks a lot. Let's give a round of applause. And then the floor is open for questions. So you can either write in the chat or just speak up.
Maybe I will speak. Okay.
I was just going to say, I don't know if there were any questions in the chat, but I'm not sure I was able to see them.
So far, no questions in the chat.
So I have okay, Dominic.
Okay, can you maybe speculate whether randomness is necessary to get this result? Does one have to go through a randomized committee rule?
Oh, you mean
or to put it more specifically, could there be like a nice voting rule that selects like the right committee? Or does it need to be something a bit unsatisfying that involves a rounding
I
step?
think that's a great question. Yeah, and that's something that I would really love to know as well. To speculate, I really don't know. I feel like our understanding of this problem is a little bit far from the truth for me to feel confident enough to be able to make a claim like that. I think that it would be really awesome if that were the case, and that's something that I'd really like to understand. Yeah. Can you find like a very simple algorithm that can find these committees? It would be very cool. Yeah,
because
I mentioned
the
that
improvement to 5 is even worse, right? It's fixed point theorem, I think, is used
absolutely.
as well.
Yeah. If you're curious about if you can find these committees efficiently, the answer is that you can, with some sort of uh, funky, no regret learning type things to kind of learn these distributions and then sample from them. Yeah, that's not very satisfying. I think it would be great if you could find an efficient, a clean algorithm for this. Yes.
Okay.
Yes.
I have a question. A classical result in social choice theory, the Nakamura theorem. I don't know if you've heard about it. The Nakamura theorem. Okay, it's generalized what you said. Basically, it's about the supermajorities. It says that the Nakamura number is a minimal
number of winning coalitions so that the intersection is non-empty. And the core of voting gain is there is a Condorcet winner basically if the number of alternative is inferior to the Nakamura number. So basically, the example you presented at the beginning are just an application of the theorem which applies to all the possible voting gains, not only the majority games or quota games. So I think a natural extension of you would be to look if you can find a kind of Nakamura type result in your setting.
Oh, okay. Nakamura, is that what the name?
Nakamura theorem. Yeah. 79, I don't remember.
It sounds familiar, but I don't remember off the top of my head. So I'll definitely look into it. I'm curious.
Yes, Nakamura. Okay. There are already some reference on the chat. Thank you.
Okay,
I
great.
think
Thank you so
there's
much.
natural connection. It's a natural connection to make to you with your talk. Yes. Thank you.
Yeah, I appreciate that. Yeah, there's just so many different definitions that are like very similar and kind of in the same vein, and many of them have like slight differences, which are actually quite subtle.
Mhm.
But yeah, I'd really love to learn more for sure. Thank you.
Welcome.
Ariel?
Ross, in terms of an algorithm for computing the Condorcet winning set,
Yes.
do I understand correctly from your proof vision board that if you take the maximal lottery and sample 6 candidates from the maximal lottery multiple times, you will get such a set?
So not quite exactly. So that's a yeah. So that's the kind of the right way to think about it. But it turns out that you need to use something slightly different from a maximal lottery, which is this thing called a stable lottery, where basically like a maximal lottery is a game where like we each pick a candidate and then sample a random voter and the voter prefers is the winner, and it's the Nash equilibrium of this game. And so if you look at the version of this game where instead one of the players can pick K candidates instead of one candidate, then the Nash equilibrium of this game is this thing called the stable lottery. It's exactly this, dice game that I was saying earlier. And so if you can sample from that distribution, then that's enough. But it's a little bit tricky because it turns out that this distribution, or this game, the strategies are over sets of K candidates rather than just one candidate. And so like actually like figuring out how can you sample this efficiently in terms of K is like a slightly non-trivial thing to do, but it was done in this previous work that I mentioned that introduced these stable lotteries. And the reason you can do that is basically that one of the players is playing a single candidate. And so you can kind of like get away with learning one of the player's strategies in some kind of sense. And I think this is like a sort of common trick in no regret learning, as far as I understand it.
Great. Thanks.
But also, I should mention that you can get some kind of result if you just sample from a maximal lottery. But it turns out that you can't get better than this 1/2 threshold. You're kind of stuck there because, like, if you think about it, in an election where you have 51% of the voters prefer candidate A over candidate B, then a maximal lottery deterministically picks candidate A. And so you kind of like get stuck at 50%. But it is true that if you sample from a maximal lottery sufficiently many times, then the fraction you get should tend to K. Or sorry, 10 to 1/2.
Sorry, can you say which fraction? I don't know what is a
The
half.
fraction of voters that prefer some other candidate over the K candidates that you pick.
Oh, so this wouldn't be like sampling 6 multiple times and taking the best choice. You're sampling more and more. Do I get that right?
So what I'm saying is that if you sample 6 times from a maximal lottery, you can get some result that isn't quite this majority threshold. And if you sample, 100, then it'll be kind of pretty close to 1/2, but it'll never cross 50%.
Yeah, makes sense.
Yeah.
Cool. Thanks.
Thanks. Yeah.
What about domain restrictions where Condorcet winners are not guaranteed to exist? Have you looked at any, and do you know if you can get better bounds than 6 or 5?
So what do you mean by domain restrictions?
Like, I mean, one example would be single peaked, and there you can always do K equals 1, right? Because you have Condorcet winners are guaranteed to exist. And then you could look at other domain restrictions where Condorcet winners don't necessarily exist and ask what's the best K for profiles from this domain.
Okay, yeah, that's a great question. Yeah, so yeah, there's been some cool work that my co-authors Adrian and Alex have been involved in, where they look at Condorcet winning sets in metric spaces, low-dimensional metric spaces. And so they show that, in I think that they have a nice result, which is like if you look at like two-dimensional metric space with the L1 norm, then you can always find sets of three candidates. And so the single peak thing is like, if you're on a line, then you can always find a Condorcet winner. And so it does turn out that in kind of low dimensional metric spaces, you can get better results. But I think that there's also still some interesting open questions in that direction as well. I see Dominic has linked the paper. So yeah.
More questions? Okay. So if not, then we'll stop here. Our next session is on check. Dominic, do you know the date? February?
It'll be in early February on a Monday.
Yeah. First Monday in February.
Yeah, it's planned for the 2nd of February.
Okay. So thanks everyone for presenting and joining, and hope to see you in the next session. Bye bye.